Welcome to EDU World Space.
So we are trying to find out this angle theta here through which the particle rotates on the surface of the sphere by the time it leaves the surface of the sphere. So our first step is to say that we know that the normal contact force at this point is equal to 0 because it's leaving the surface of the sphere and therefore is no longer in contact with the surface of the sphere. This means that the only force acting on it is the centripetal force, which acts in this direction. And we know that that must be equal to the component of the gravitational force, so the mass of the object's induced force, which is equal to the mg multiplied by that theta to obtain it and resolve it in that direction. So what we can start by doing is equating these, so saying that the centripetal force equal to mv squared over r, in this case, is equal to the mass of the object multiplied by the gravitational constant and then resolved in this direction. So what we can see is that as these are two parallel lines, this angle must also be equal to theta. So resolving this, we know that the component in this direction is mg cosine theta. So what we can do now is neaten up this equation by cancelling out these m's and taking this r up to this side. So the expression we're left with here is equal to v squared equals rg cosine theta. So our next step is to say that we know that energy must always be conserved. So this means that whatever change in kinetic and potential energy occurs between point A and B must be equal. So we can say that delta Ke is equal to delta Pe. So the way we do this is saying that the kinetic energy initially, or at the final state, is 1/2 mv squared. And it's equal, this is the change in kinetic energy here, to the change in potential energy, which is given by this height here. As can be seen, this is a vertical height difference. And again, the way we obtain this is by saying that it is equal to r, which is the radius here, minus r cosine theta, so that we can get this length here, as r cosine theta will provide this length here, which is adjacent to the angle, and subtracting that from the total radius will provide us with this length here, which is what we're trying to obtain. So r minus r cosine theta, which is the difference in height, again multiplied by mg. So this is our second equation. So what we can do now, again, is neaten this up by just cancelling out these masses. And we know from this first expression here that v squared is equal to rg cos theta. So we can sub this into here for v squared. So now we can neaten this up and say that 1/2 rg cos theta is equal to g r minus r cos theta. So what you can do now, again, is a little bit more cancelling, and we can see that r is common on each side, so we can just take this factor out, and that g is also on each side, so we can take that out. So what we're left with is 1/2 cos theta is equal to 1 minus cos theta, as it's all cancelled out here. So then what we can further say is that taking this term onto this side, 3/2 cos theta is equal to 1. And therefore, cos theta is equal to 2/3. And then just inverse cosigning this 2/3 can give us the final angle, which is equal to 41.8 degrees, or also equivalently 0.84 radians. As our final answer.